Section 21.3. The nucleophilicity of the entering group. The nucleophilicity is a measure of how fast or slow the association reaction between the entering group Y and a transition metal is in the ligand substitution reaction. So this entering group Y is going to replace a leaving group X in this ligand substitution reaction. Quantitatively, the nucleophilicity of the entering group Y can be expressed in terms of a nucleophilicity parameter, N sub Pt. This N sub Pt is the logarithm of the ratio between two rate constants. On top, this is the reaction rate constant of the association between Y and the transition metal in a complex. Over here, similarly, it's the reaction rate constant between methanol and the same transition metal in the same complex. So we're looking at a ratio here. What's the value of N sub Pt for methanol? It's 0. Because if you imagine this Y is methanol, on the bottom, this is also the rate constant of methanol, you get a ratio of 1. The logarithm of 1 is 0. Therefore, this nucleophilicity parameter, NPT of methanol, is simply 0. Methanol is used as the 0 reference. And this K2, again, is the reaction rate constant of this reaction. The reactant is trans dichlorido dipyridine platinum with an oxidation number of 2. Y is the entering ligand. Y is about to replace one of the two chlorido ligands. We just measure the reaction rate constant for this one. And then we compare this reaction rate constant when we have methanol here instead of Y. That's our reference. So again, this NPT is just relatively how fast this Y can be bonded to this platinum transition metal center in this complex relative to methanol. And it's the logarithm of the ratio. And because of this equation, we can easily tell the logarithm of K2 of Y is simply NPT plus the logarithm of this K2 of methanol. Right? So we can rewrite this equation, and we'll see this logarithm of K2 of methanol can be expressed as a constant. So it's just constant C here. Now let's change the complex. We do not always have to have this 2 pyridine here and 2 chlorine here. We can use some other transition metal complex. But similarly, we're going to use this entering group Y to replace one of the ligands in the reactant transition metal complex. So in general, we'll just do this. We'll say this PT is bonded to 3 ligands. They can be any ligands. And X is the leaving group. Y is the entering group. And we're going to just measure the reaction rate constant, assuming this is going to be second order. So we're going to have the slowest rate limiting step that involves the reaction between this Y and the complex. This Y is going to form a bond with this platinum center. And in this case, we can again measure the reaction rate and then calculate the rate constant. And we find that this logarithm of the reaction rate constant is still proportional to this N sub Pt. So this N sub Pt is determined in this reaction when we use dichlorido dipyridine platinum as the reactant. So we can use some other complex with the same platinum center, and we get a linear trend as well. And it's really interesting that this S is usually close to 1. Okay, so if you use some other ligands, S usually is close to 1. How close? I would say like between 0.5 and 2. All right? And also plus a constant. So this is the slope. This is the slope. This S is called the nucleophilic discrimination factor. It characterizes the sensitivity of the rate constant. So this is the rate constant, and S is the sensitivity here of this, how sensitive this rate constant is to this NPT. And again, NPT is the nucleophilicity of the entering group Y. And this NPT is determined for this specific reaction. Okay, Y react with trans dichlorido dipyridine platinum complex relative to methanol. That's the definition of this NPT right here. All right. So this sensitivity tells us again how significantly does this rate constant for this reaction depends on NPT.